All right, we'll get started. So here we are in chapter 6. We're going to start off with solving systems by graphing. What we're talking about systems is to go a little bit simplistic. We are dealing with equations. Okay, typically we've dealt with one equation and then we would graph it. Now we're going to be looking at two equations, which is called a system, and we're going to see how they interact with each other. Okay, what we will end up noticing is how when they have a point in common, that is the point in which they intersect if you were actually to graph them. We're going to find several different ways to actually solve these systems. So the first we're going to start off with is graphing them. Okay, so that's where we start off with 6.1. We're going to look at, okay, so we use the word solution. What does solution mean? Whenever you have an equation, what does solution mean? Sure, the answer. Or another way of thinking about it is what value or values, especially because we're going to be dealing with x and y, what value or values make this statement true? What's interesting is we're talking about values for x and y, and whenever we graph, we use x and y to find coordinates so that we know what to plot on the graph, right? So then once we find these values, then we can plot them, and then we can connect points, and we can assign different values for x and y and solve for the equation and see exactly what we're looking at, okay? All this will come a little bit more clearly as we start processing through all of this. So, again, the first method we're going to go over is graphing. Let's look at page 218, and we're going to do example 1 first together. Okay, we're going to do example 1. Now, whenever we start this, notice we have these two equations, x plus y equals 4, and then x minus y equals 2. What we want to do first is put this in slope-intercept form. Is that correct? Do we know what slope-intercept form is? Slope-intercept, do y'all remember that term? What's wrong with what I just said? Anybody? Should I have said it a different way? Does the word slope sound familiar? Does the word intercept sound familiar? Have we heard them put together, slope-intercept? Good job. No. We can find the slope, okay, but the form we're actually looking for is y-intercept form. Is that right? Are you sure? No, because it's confusing. Look in your book. Look in your book. Okay, and I bring this stuff up because I want things to become familiar. You can hear slope. Oh yeah, I remember talking about it. But I forget what it is. And then there's y-intercept. I remember that, and I know that I should know it, and I remember doing something about it, but I really can't tell you anything beyond that. So and then we talk about slope-intercept, which actually is a term. So, but I bring all this stuff up because if you think about it, I want you to be able to relate to something else. Yes, not only do I remember talking about it, but I know how to do it because of this. This thing reminds me of what we were talking about, okay? So, now you can go back and think about this whole confusing conversation we just had. Does slope-intercept sound familiar? Like, no, wait, no, it does. Because there's y-intercept, and there's slope, and then there's slope-intercept, okay? What is a slope-intercept form? Do you know? Let's say we have this equation here. How would we move them around to put it in slope-intercept form? Yes, very good. So slope-intercept form is y equals mx plus b. Okay? So all we're doing is we're putting y all by itself on one side of the equal sign. So we will take this one and we will take y equals 4 plus x. Okay? Is that correct? I saw two people shake their head no. What's wrong about that?
Should it be x plus 4?
It can be. But is that...
Wouldn't it be negative? Like,
What's negative?
Yeah.
What's negative?
Well, yeah.
Very good. The x minus x plus 4. Okay? Or you can write it y equals 4 minus x. That doesn't matter. Okay? Just like this could be y equals x plus 4. It doesn't matter. But this is incorrect. Because whenever we move this x over from here to here, we have to do the inverse operation. So we have to subtract x from both sides. Very, very important that we do that. Otherwise, we end up with wrong answers. We have to pay attention to our minus sign. So let's get back to where we were. All right, so y equals negative x plus 4. Okay, now what we can do is we can assign values on, now this is a linear equation, meaning we're using an equal sign. Okay, how many points do we want to have in order to kind of verify exactly how this line, or making sure that we're accurate with our calculations?
At least 3.
At least 3. Let's at least have 3 points. Now, what we can do in order to graph this, we have our graph. We need to have x values, and we solve for y. Okay, so we can put in anything we want to. We can put a 0 in for x, and y equals what value?
4.
4. Very good. Whenever we plug in 0 here, we substitute this x and put in a 0. We finish it out and solve for y. What does y equal when x equals 0? Well, y equals 4. Okay, well, what about if we use a 1? Okay, well, then it would be minus 1 plus 4, which equals 3. So when x equals 1, y equals 3. Let's throw in a negative 1 down here. Equals what will be our answer here? We have minus x, so whatever x is, we have to say minus, and we're using a negative, minus a negative 1, 5. Very good. So now we have 5 for y. So here we found our coordinate points, and we can graph this. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the first one is 0 when x is 0 and y is 4. When x is 1, y is 3. And when x is negative 1, y is 5. And so this is our line going this way. Okay, so that's our first one. Now the next one we can do the exact same way. Okay, does everybody understand what we did here to get to this point? If not, please shake your head side to side, no, I don't understand, so that we can go over it. Okay, everybody good? All right, so we handled this equation, this first one, we've got it done, so we can check it off, and we've graphed it. All right, so now we can do the same thing with the second one. I'm going to erase this. Everybody has all the information. First, we have to put it in our slope-intercept form, which means y needs to be all by itself. So whenever we move this x minus y equals 2. This one looks a little tricky because we have a negative in front of the y. So we're going to have to do a two-step process with this. Y needs to be positive, okay, to make life easier. Doesn't have to be. We can, it's going to cause less problems if we get it to where y is positive starting off. All right? So let's move y over to this side. Okay, let's do that. So adding y to both sides, so x equals 2 plus y. All right, well, y still needs to be by itself, so let's move the 2 over to this side. So minus 2, so then we have x minus 2 equals y, or we can flip them on either side of the equal sign however we want to. Y equals x minus 2. Both are saying the same thing. No matter how you flip-flop it, it's saying the same thing as long as you don't change what is actually being said. Okay? All right? As long as you say the same thing, you can say it forward or backward. Does that make sense? The ball bounced on the ground. Bouncing on the ground was the ball. There's a different way of saying it, but it's the ball and it's bouncing on the ground. Okay, so here we have it in our proper form. Now again, we find values for x and y, and then we go on from there. Okay, so x can be 0, y is negative 2, x can be 1, and y is negative 1. We can do negative 1 for x, and y will be negative 3. So we have 0, negative 2, 1 and negative 1, and then negative 1 and negative 3. So we've graphed it, and then we see what type of relationship they have with each other. Okay? So we've graphed these 3 points, lines going this way. Here, we have the point at which they intersect. What do you think? Think about this coordinate point. What could you do with that relative to these two equations, and what information would it tell you? What do you think would happen? So they connect at this point, and this is some coordinate point, okay? There are some coordinates that this fits inside, okay? And which means you have an x value and you have a y value for those coordinate points. What does that tell you, or what can that tell you in relation to both of these equations? Here we see this is where they intersect. What does it tell you about these two equations, that one point?
That it satisfies one.
Very good, yes. So think of it this way. If you picked any point on this line or on this line, and it fell on that line, it's going to, let's say this one in particular, this line here, any point on this line, you plug in that x and y value, and it's going to say that this statement is true. Okay? You can do x is 98, y is 96. Well, 98 equals 96 plus 2. And so that is true. So anywhere on this line, you can plug it into this equation, and it'll give you a true statement. It solves this, or it gives you a true statement. Same thing with this one. Well, what's interesting is that point at which they intersect, that coordinate point will satisfy both of those equations. So that coordinate point, whatever it may be, x and y, you can plug it into either one of them, and it will result in true statements. Now, graphing gives us a visual idea of this taking place. The problem with graphing is it may be very difficult sometimes to find out exactly what that coordinate point is, especially if it's in between those hash marks. You're like, okay, is it 2.5? Is it 2.6? You know, or is it actually on the 3? You know, a lot of it's very visual. And is the graphing accurate? Am I seeing it on a 3 when it's actually, it should be a 3.5? Does that make sense? So graphing gives us that visual idea. However, we will be able to solve in other methods that will be more accurate. So it's just a way of doing this. Make sense so far? Any questions? Okay, so that's graphing. Let's move on to 6.2. All right, 6.2, we're going to solve these systems by substitution. Okay? Understanding that the solution to most systems of two equations with two variables is the point where the two lines intersect. Okay? Some system involves lines that don't intersect at all. Okay? So what would, if these lines don't ever intersect, then would you ever have coordinate points that would solve both equations? What do you think? No? No. So if those lines never ever intersect, you will have a point that can solve one of them or the other, but there will never be that one that actually solves both of them. Okay? Now, what if you end up graphing them? Okay? Put a graph over here, and you ended up drawing a line here, and then you did your other equation, and you drew your line, and it ended up going exactly on top of that other line. So how many possible coordinate points would satisfy both of them? Yeah, it can be an infinite number. Okay, since these are lines that are going infinitely in the other direction, if any point solves one of the equations, that same point will also solve the other, and it's an infinite number of them. So now we're looking at three possibilities. One coordinate point, wherever they meet, okay, that satisfies both. You could have where they never ever intersect, and so you have no solutions for the system talking about an interaction of two equations. Or you can have an infinite number of solutions because those lines lay exactly on top of each other. Okay? Make sense so far? All right, good deal. As long as you keep those three possibilities in the back of your mind, then that will be very helpful. It's kind of like directions. If I wanted to go to Starbucks, and I know my friend is going to go to Starbucks, and they live around the corner, well, I go one way, they go another, but inevitably we end up going through the same intersection to get there. Okay, that's one point that satisfies that. Or, man, I go down this road, they go down that road, and then we end up actually going to two different Starbucks. Okay, so you never ever cross paths. There is no solution for that. Y'all will never meet up. You can't ever talk because you're both at the wrong Starbucks. Okay, and you went different ways.
Struggle wheel.
Yes. Or you are like BFFs and y'all walk out the door together and you drive single file right behind each other. Obviously you don't carpool because that just wouldn't make any sense. But you drive right behind each other and follow the same path all the way to the same Starbucks, so y'all have an infinite number of possibilities to solve that solution, okay? So there's a different visual behind what's going on. Okay, so now understanding that, let's go into what substitution is, okay? We are going to take, since we're talking about these two equations here, and I think the books is different. Starting off, I want to use these same two, okay? These same two here, and then we'll go to the book, or to the book's example 1. So what we're going to do is, again, we're going to get y, and it really, in this situation, it doesn't matter which you do. You can get x by itself or y by itself. What it depends on is what's going to be easier for you. And we'll understand what I mean by that here in just a second. Okay? So let's start off where we have y by itself. We're going to rename it. Y equals 4 minus x. Okay? So we've adjusted that. We have now essentially assigned a value for y. Y equals 4 minus x. Okay? We don't know a definite single integer number for this yet, but we will find that out. But we know that we can take y, pull it out, and actually substitute this value in place of y in another equation. Well, let's take our second equation, x. Okay? So x minus, and we can take our value for y, plug it in here, 4 minus x, and then that equals 2. Do we see how we got to this point right here? We took this equation, we took out y and put this value for y in place of it and finished out the equation. Now, we have to pay attention to this negative sign. Okay, that negative sign applies to everything that is the value of y. That's why we put it in parentheses, so that we don't make that mistake. Now, let's get rid of the parentheses. X minus 4, and then minus a negative x gives us a positive x equals 2. Well, if you've noticed here, now we've gotten it down to where there's only one variable. That's really easy for us. We've done this all day long, every day, for the past however many years, right? So we can combine these. X plus x is 2x, minus 4 equals 2. And then we're going to add 4 to both sides. 2x equals 6, dividing 2 on both, and x equals 3. Okay? Everybody caught up with where we are here? Well, now we have an actual value for x. X equals 3. Now we can go back into either one of these two equations, plug in, substitute x for 3, and find out what the value of y is. Okay? So let's do the top one. We'll do, I'm going to go over here, 3 plus y equals 4, therefore y equals 1. Well, let's try it on this one too. Let's put x over here. Okay, so 3 minus y equals 2. Well, we subtract 3 from both sides. And minus y equals a minus 1. Well, y has to be positive, but we can multiply both sides by a negative 1 to get positive. So y equals 1. So notice how 3 solves both of these values. We get the same value for y. So now what we found is whenever we graphed that earlier and we saw where they connected, it's whenever the x-coordinate is 3 and the y-coordinate is positive 1. That coordinate solves both solutions. Okay, it solves the system. Okay, so what we did, this is called substitution. Again, we move everything over, and again, you can do this with x. You could move the y over and then substitute that in for y, or for x. Yes, go ahead.
I have a question. Back over here, you minus the 3 from the y side, and then it's negative y, but then on the next one you have positive. How did...
Yes, because whenever you, it's a negative 3 plus 2 is negative 1, and you have a negative y.
So they just cancel each other.
Yes, basically you need a positive value. Y has to be in positive form. So in order to do that, you have to multiply both sides times a negative 1.
Oh, okay.
But as long as what you do to one side you do to the other, then it will make a positive y equals a positive 1.
Okay.
Good question, though. So let's do another one. Let's do example. We'll do example 1. 3x plus y equals minus 20. and y equals x minus 8. Now here in this example, it made it easy for us because y is already by itself, so we can use this equation for our substitution. Okay? If we wanted to, and we felt it was easier, we could take this 3x plus y equals 20.
Negative 20.
Is it negative 20? Oh, thank you. Negative 20. And let's say that we just have this bad attitude about y and what it does, and so we like x being by itself and we always want to shove y off to the side. Well, we can do 3x equals negative 20 minus y, and then x equals minus 20 minus y, all that divided by 3. And then we could plug this value in to any one of these equations in place of x and solve for there. Okay? Doesn't matter which one you're substituting is what I'm trying to bring up. Okay? It does not matter. Sometimes you may see a situation like this where x plus 2y equals 10, and let's say this was 2y. So let's look at this. Here we have 3x plus 2y equals negative 20. X plus 2y equals 10. Which one of those equations do you think that you're going to want to use to get one of those letters by itself with nothing attached? To be substituting in?
Second one.
The second one, okay? It's easy because we can identify this x has nothing attached to it, and it's easy for me to just move the y over instead. So we can have x equals 10 minus 2y. As opposed to going this route, using this, you're going to have to do division, and you're going to end up with a fraction. Okay? So find the one that is more simple for you, then get whichever variable you want by itself that's going to be the easiest, so that you have it by itself, and then you can go in and do all of your substitution. Make sense? Yes.
How did we get the 2y equals
I just made that up.
10? Okay, I was like,
Just to show an example, we're gonna go back, and I'm going to adjust this according to the book. But I was just giving an example. You don't always have to say y equals, whenever you're doing substitution, it does not always have to be y equals something. It can be x equals something, and then you substitute for your x's. So, y equals x minus 8. Well, we're going to use this one right here because it's already set up for us. So we'll plug our value for y into the other equation, plus x minus 8 equals minus 20. So we have 3x plus x minus 8 equals minus 20. So 4x equals, and I'm going to add 8 to both sides, minus 12. Everybody see how we got from there to here? Kind of skipped a step. Okay? And then we're going to divide by 4 on both sides. So x equals a minus 3, because remember, this is negative 12 divided by positive 4 is a negative 3. So we now know that the x-coordinate is going to be a negative 3. Now we can take this negative 3 and plug it into any one of these equations and solve for y. Which one do you want to plug it into? The bottom one, because that's a whole lot easier. All we got to do is put negative 3 in here, and we find that y equals negative 11, because a negative 3 minus 8 is negative 11. Why plug it in here and do more math than we have to, right? So then our y-coordinate is negative 11. Now, in order to check our answer, we can plug it into both of these equations and make sure that we come up with the same answer. So let's go ahead and do that. So we'll move over here. 3 times a negative 3. We're substituting x for negative 3 plus y equals negative 20. So minus 9 plus y equals negative 20. All right? We will add y to both sides, or add 9 to both sides, and find that y equals negative 20 plus 9 equals negative 11. We have our same values for both, so that's the way we've checked our answer. And this is our coordinate point, the point at which those two equations intersect. Okay, it solves the system. Make sense? Sometimes it takes a little bit more movement to get to a variable that is all by itself here. Okay, then sometimes that's necessary, but that is the goal through substitution. Any questions about that so far? Cool. Let's move on to 6.3. Oh, let's go back a little bit. I do want to go over to on 6.2. Just for definition purposes, so you understand, the solutions, the ordered pairs that are solutions are called consistents. Consistents. Okay, consistents. All right, whenever graphing and we find that they are parallel lines, they never intersect, they are called inconsistents. Inconsistents, and then whenever we're dealing with sets of ordered pairs, what would that be called? If there's nothing to fill in to those sets of ordered pairs, nothing exists, what's that called? Remember what kind of set? What's that?
Empty.
Null or empty set, both are correct answers. Very good. Okay, good deal. All right, now we can move to 6.3. I forgot to bring that verbiage up. Okay, now we're going to be doing a system called adding. Okay, we're going to solve by adding. The whole idea is to align them up like you normally would whenever you add numbers. Okay, think of it as if you're adding decimal places, you always put the decimals in line, and then you put everything else consistent with it. And whenever you add the ones together. You add the tens together, the hundreds together, to get an accurate answer. We're doing the same thing. We're going to be staggering them so that our x's are in line, our y's are in line, and our constants are in line. Okay? So let's look at example number 1, and we'll see what we're talking about. Whenever we are adding, the goal behind this is, and especially whenever you recognize, because you're going to be given systems, and then you're going to have to determine, should I graph it? Should I use substitution? Should I use adding, or should I use some other method? Okay? Looking at it, you'll be able to see, you know what? I think adding is going to be easier for me to do this, and so I'm going to use adding on this one. And the whole idea behind this, and understanding different methods, is to make life easier on you. Do we like it whenever math is easier for us? Yes, we do. Yes, we do. All right, so this method, the idea behind it is to eliminate one of the variables. So let's look at this. X plus y equals minus 1. And 2x minus y equals 10. Notice that our x's are lined up, our y's are lined up, and our constants are lined up. So, doing this, we can draw a line underneath, and we can add them together. What happens whenever, well, before I go there, understanding we say or use the term adding, but what's taking place is technically subtraction. But adding, whenever you add a negative, that's the same thing as subtracting. Okay, so they call it adding because adding is what's taking place. Just realize that whenever you add a negative, it's the same thing as subtraction. Okay, so whenever we add x plus 2x, we end up with 3x. Now here we have positive 1y minus a y, which gives us what?
Negative.
Negative what? What's 1 minus 1? 0. Plus 0 equals, and then 10 minus 1 is 9. So here in this situation, we now have 3x equals 9. We can divide by 3. X equals 3. What happened here is because we aligned them up, and we were able to eliminate, or we can identify where adding a positive times that plus the same negative of that number gives us 0. We've eliminated one of our variables, and now we're left again with one variable. And from there, we can find a value for x, and then substitute that into either one of these and find the value for y. All right, so we're using addition and really subtraction at the same time, okay, to eliminate one of them so that we only have one left. So let's do this. What if you had y plus 4x equals 2, and you had minus 4x plus 2y equals 7. Okay? Well, looking at this, we want to align these up, and already if we were given these two, we could graph it, we could substitute, but then we can look at this and say, you know what, I have a positive 4x in one and a negative 4x in the other. That can be eliminated. I can get rid of those x's if I use addition. Let me line them up correctly. Y plus 4x equals 2. 2y minus 4x equals 7. Well, then that gives me 3y. This is 0 plus 0 equals 9. Well, that's 3y equals 9. And y equals 3. Heck, that was easy. Does that make sense so far? Now, first of all, are there any questions about this? All right. What we can do, and this is kind of a step further with the addition method, what if this were a 2x right here? If this equation was 2x minus 2, okay, let's just say you were told you have to use the addition method to solve this. All right, well, let me first line these things up. Y plus 2x equals 2, and 2y minus 4x equals 7. Well, I don't have anything that I could substitute or do the addition method and end up with nothing. But what can we do to equations as long as we don't change the actual statement itself? If we don't change the results, can we rename? Sure. If we have Bob, as long as we don't change anything about him, we can name him Jim. And it's still Bob, we just renamed him Jim. Okay, we changed nothing about it. Okay, we can rename one of these to make it work for us. Okay, so can somebody see what we could do that as long as you do to all terms can make it to where we can use the addition method? Let's focus on this equation. How could you change this equation to make it fit here? To where we're not changing it into this equation, we're just going to rename this to where we can use the addition method. What's that?
Add 2.
How would you add, where would you add to? You're on the right track,
All of it.
because,
Because what you do to one, you have to do to all of them.
okay. So would we add to, or what? What do you think?
We could subtract 2 from the right side, make that a 0. Oh, no, it worked. Never mind.
Now, what we're trying to do is rename this whole thing to where either our y or our x's are the same so that we can subtract the other one from it and result in one of them being 0.
But you would add 2. Why?
Okay, so, okay, I see what you're saying. So, we will have 2y plus what?
4.
Plus 4x
Oh,
equals what?
4.
4, yes. So we got to do to all three terms. So we renamed this. Now we have 2y minus 4x equals 7. Now we can actually get rid of our x's because we have actually, sorry, I say 2. Both of them are 4x's, but we have one positive, one negative. We are adding 4x and subtracting 4x. Okay, so here we have 4y plus 0 equals 11, and then we can go on from there. We now have y equals 11 over 4, and then we can plug it into either one of these. So realize you can rename one of your equations to make it work. Just make sure that you are doing it to all of the terms. If you make one change, you have to change all of the terms. Pretty easy, right? Not too hard. And this, you wouldn't think, you might not have thought that you could do this, but it's something that's very easy, something we've done for a long time, and it makes our life a lot easier. A lot of people will end up finding that they like to do the addition method better. Other people like to do the substitution method better. If it's real easy, then I'll do the addition. Me personally, I just like to do substitution. To me, I don't know why, it's fun for me. It's kind of sick, but whatever. I like that. So it's just the way of moving stuff around. That's how that process is in my head anyway. So, all right, any questions with that so far? All right, good deal. Make sure your biggest issue on this is going to be dealing with your signs, okay, your positives and negatives. Pay close attention to those, please, please, please. Okay, even with substitution, that's what's going to end up throwing most people off if you end up making a mistake, okay? All right. Now we have problem solvings, okay? 6.4. All right, we're going to use example 1, and we're going to use what we've learned so far to apply it to a word problem. So let's read this off. 2 buses, 412 miles apart, head toward each other. One travels 3 miles per hour slower than the other, and they meet in 4 hours. What is the average of each bus, the average speed of each bus? How many unknowns do we have in this problem?
Too many.
2.
2. What are the 2 things we're trying to find out?
Well, how fast one is going to so good.
Exactly. We're trying to find the speed of both buses. We don't know either, okay? We do know some information about it. We know that one is traveling 3 miles per hour slower than the other. So what kind of comes to mind already as far as labeling unknowns? Let's say we have bus 1 and then bus 2. What is bus 1 going to be as far as x? Very good. What is bus 2 going to be?
4.
X minus 3. So it's bus 1 minus 3 miles per hour slower. Does everybody see how that happened? We have an unknown, and now, I don't want to confuse anybody, but another way of saying this would be, we could make bus 2x and bus 1, x plus 3, as long as we stayed consistent with that. Okay? I already see some heads shaking. No, don't do that to me. So, all right. So we'll keep it like that. We have one unknown, and we know that the other bus goes 3 miles per hour slower than that. Okay? Now, what's interesting is that's how we've considered things in prior word problems, how they relate to each other. Okay? Now let's do this. We've been talking about using 2 variables in our systems to come up with information. Okay, so let's try it this way. And we have our fast bus and our slow bus. Okay, just to kind of follow along with what the book is saying. Okay, in fact, we'll keep it. I'm going to switch them because it even does it this way. Slow and then fast. We're going to create our chart, as we should always do whenever we're doing word problems. Now, distance equals rate times time, right? Distance equals rate times time. Whenever you do your charts and you have a formula, put it up top and even put what type of math is taking place. If you're adding, subtracting, multiplying, dividing, put that up there so it helps remind you as you start plugging in all of your information. Here, we are using a value of x for the slow bus and y for the fast bus. We are now incorporating 2 variables, 2 different unknowns. But what we've already found out is we can have 2 variables, come up with information, and use 2 different equations to help ourselves solve this problem that we're dealing with. Okay? We found it's actually pretty easy to do. All right, so we know that both are traveling 4 hours. Okay? And their distance is going to be rate times time, so it's x times 4, or 4x, and 4y. Now, what do we do with this information? Okay, we know that similar to what we were talking about here, that y is the same thing as the slow bus minus 3 miles per hour. Okay? Fast bus, okay, y, we know that as actually going 3 miles an hour slower, okay, than, hold on a second. Yes. No, sorry. I'm an idiot. X equals y minus 3. Because the slow bus obviously goes slower than the fast bus, right? Yes. So, our slow bus is actually going 3 miles an hour slower than the fast bus. Okay? We all on board now? All right, good deal. Now, what total distance are they going? Do we know?
200.
Okay. They are both traveling together 412 miles per hour. They're starting at some point, okay, and they are going to end up meeting up, and they both travel together 412 miles per hour. Okay, so how can we combine their information in relation to 412 miles? What do you think is happening with those buses? Are they going to multiply their speeds to get 412? Let's say they were both going at the same rate, 2 different places apart. How far could you figure that each of them are going to go? If it's they're still traveling 412 miles per hour, or they are going 400 super speed. They're both traveling total 412 miles, but they're both going the same rate. So how far will both of them end up traveling each? All right, we'll skip past that because I'm getting some blank stares. So let's look at this. We have the distance of the slow one plus the distance of the fast one is going to equal what? The distance of the slow one plus the distance of the fast one is going to equal what?
The total distance.
Very good, which is what?
I actually got that right.
Which is what? 412.
Yay.
We are told, and this is one of the difficult parts that I find people have with word problems, is grasping this concept, which is actually very, very simple. Okay? And a lot of times you have to stop and think about what it is that they're asking you. I've got two buses. They're apart from each other, and they are, once they meet, they will both have traveled 412 miles per hour. So if you think of a string that is 412 feet apart, okay, and you have two little buses that can slide back and forth on that string, and they both start at the end. Whenever they meet and you hold them together, no matter how you move them back and forth, they are still traveling along that 412 feet. That 412 feet string doesn't change at all. Okay, one can go 1 foot, the other one can go 411 feet. Okay, or they can both go 206 feet. But to combine, no matter how you move them, you add their distances together to get that 412. Okay? Got it? Still no. Okay. We'll move on. Okay, so when you add their total distances together, we are getting 412. All right? Now, what we can do is use these two equations that we've come up with, and we can combine these together. We know that the fast one plus the slow one, or the slow one plus the fast one, equals 412. We also know that the slow one is traveling 3 miles an hour slower than the fast one. Well, here we can use whichever method we want to from what we've learned. We can use graphing, we can use substitution, or we can use addition. Here we're looking at these two equations, x equals y minus 3, and 4x plus 4y equals 412. Substitution is most likely going to be the one that we want to use because it's already set up that way. Okay? So we can take out x and plug in this value for y in place of it, and then solve for y. So it'll be 4 times y minus 3 plus 4y equals 412. So it gives us 4y minus 12 plus 4y equals 412, and then so on until you find out your value for y. Once you find your value for y, you can plug it into either one of these and solve for x. Okay? Then, as we do this, you go down and find that y equals 53 and x equals 50, which just so happens to be 3 miles an hour slower than the fast bus. Okay? So, word problems again, use your charts, plug in the information that you know. This one is going to be, if you think of it in terms of trying to come up with one using two variables and come up with two equations, then solving it is actually going to be relatively easy. Okay? But understand the problem, understand what it's asking. Let's look at number 2, page 234. We're not going to go through this completely, we're just going to talk about setting it up. Okay? Mr. Perry has a total of $10,000 invested in 2 accounts. The older account pays 8%, while the new one pays 10%. how much does he have invested in each account if his total annual interest income is $850? Okay, he has two accounts and he has $10,000 invested in both of those accounts combined. So if you have account X and account Y, what would one of your equations automatically be? If you have two accounts that total $10,000, what could you say about those two accounts?
X plus y equals 10,000.
Yes, if you add one of your accounts, the amount, no matter what they are, it can be anything, but whenever you add one account with the other account, you know that that's going to equal $10,000 because that's what he had to use to put into two different accounts. Doesn't matter how it's distributed, doesn't matter one difference, but you know that X plus Y, or account 1 plus account 2, is going to equal 10,000. So we know that one of our equations is going to be X plus Y equals 10,000. Okay, so we got our first one down. Then we know that one pays 8%, the older one pays 8%, while the new one pays 10%. Okay, so then we can use 0.08x plus 0.10y equals, and both of their accounts, he has invested, the total annual interest income for both of those is $850. So, from both of those accounts, the total interest he has earned is $850. So again, we're going to add those two accounts together to get $850. So we have 0.08x plus 0.01y. Okay, yeah, I'm sorry, 0.10y equals 850. So now we have our two equations, and then we can work those through, okay? On something like this, especially when you're dealing with decimals, go ahead and adjust the numbers so that you're not still dealing with decimals, all right? So you have 0.08x plus 0.10y equals 850. We're going to ahead and move everything over two decimal places, so you're getting rid of all the decimal places. So you have 8x plus 100y, or yes, plus 8x plus 10y, and then you will now have 85,000. Don't just adjust the decimal places on where the decimals exist. Even though there's one that's a whole number, you have to adjust it also. Whatever you do to one term, you have to do to all the terms. Okay? And then work through it from there. All right? Now, let's go to 6.5. Quadratic systems. We've studied how to solve systems of linear equations by using three different methods, okay? And we can use the same three methods to solve quadratic equations. Okay, quadratic equations. What are quadratic equations again? We've heard the term, like, yeah, I've heard that, and I should know it. Let's see if I do. What elements define a quadratic equation? In your quadratic equation, there is an A, B, and C that would exist in the standard form. Yes?
And A can't equal 0.
Very good. A cannot equal 0. What is A attached to?
X squared.
X squared. What is special about the x squared? As far as quadratic equations are concerned? What is the highest degree term that can exist?
Yeah, I can more than
More than what?
X squared.
Squared, yes. The highest degree term can only be 2. Okay? Now, remember that we have come across some equations where there was an x cubed, but we can factor out on a lot of those equations an x and turn it into a quadratic equation. Okay, so if you come across where there's Let me show that here. If you have x cubed plus 2x squared plus x equals 0, well, we can factor out an x out of all this, and you have x squared plus 2x plus 1 equals 0. Okay? So in here, we're thinking we have x cubed, it's not a quadratic equation. But then you're like, oh, you know what? I can pull out an x out of all of it and turn it into a quadratic equation. So just keep in the back of your mind that possibility exists. Okay? So here we're going to use the same methods we were just talking about, but we're dealing with quadratic systems. So let's look at the first example and see how. We have y equals x squared plus 1, and then we have x minus y equals -3. So without looking at your books right now, just look up here. Give me some ideas of how you think, like first of all, which method would you like to use to solve this system?
Substitution.
Substitution? Who agrees? Who thinks substitution? Who would like addition? Addition. Okay. Who would like graphing? Didn't think so. So maybe no for graphing? All right. So let's look at substitution first, and then let's look at addition and see how this goes down, okay? So substitution, what do we want to substitute? Which one do we want to use? Which equation, 1 or 2, to put in a form that we want to use to begin the substitution process? 2?
2, yeah.
Okay, and what do you want by itself, x or y?
Y.
So you want y by itself on one side of the equal sign. Sure? No, I need more conviction. I need definite.
What would you do? Why don't we just add a z?
A z. You know what? It's funny you ask about that because we will be doing that a little bit later on. There will be three term that we'll be using, and it's because we have three. It's a system of 3 equations, and we involve a z, and you use the same methods. So let's do this. Let's do. You know what? We'll do y since you said y. So minus y equals -3 minus x. Okay, that's not fun. Let's get rid of the negative in front of the y. We're going to multiply every term times a -1 so that we have y equals 3 plus x. Does everybody see how we transition from here to here? Okay, now we're going to plug the value of this y up here so that we have 3 plus x equals x squared plus 1. All right, we need to be moving all of these over because this is going to end up equaling 0. So we have 0 equals x squared minus x minus 2. Okay, so then we have x minus 2 times x plus 1. This is what we have here. Does everybody see how we went from here to here? Okay? Because again, what factors of -2 when added together give you a -1? Well, our only factors are 2 and 1, but one of them's got to be negative, and this, it has to result in a -1x, so we have -2 and -1. So, now what we do is, sorry, making sure I'm not passing anything up here. Okay, good. So then we find that our values for x are going to be x equals 2 and x equals minus 1. Okay? Because whenever we actually solve this equals 0, then what makes this 0 is a positive 2. What makes this 0 is a negative 1. Okay, so just as before in quadratic equations, we end up with 2 possible answers. Well, here we have 2 possible answers. There's 2 values for x, which means we're going to have 2 values for y, right? Okay, so same thing, we can plug in this 2 for x and find out what y equals. Okay, so let's do this. We have x equals 2 and x equals minus 1. So let's do this one first. Again, the 2, and we can go ahead and plug it in here because this one's actually really easy. Because y equals 2 squared plus 1, which equals what? What's 2 squared? 17. No, it's not 17. 4, right? Plus 1 is 5, so y equals 5 on this one. What about this one, negative 1? What is negative 1 squared? 1 plus... yes, very good. Yes, the answer is 2. So our y equals 2. So here, our coordinates are going to be 2 and 5, and minus 1 and 2. Okay, or we have our 2 values that solve this system. Make sense? So, if you look in your book, we can talk about what's going on. Because remember, whenever we graph quadratic equations, we end up having a parabola. Okay? And in this instance, what